Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to show you how to write molecular, complete ionic, and net ionic equations for weak and strong acid-base reactions. And so let's get into this. So in this video we're going to go over sodium hydroxide reacting with nitric acid. So one of the things you need to recognize is that we have a strong base here reacting with a strong acid. And so that's going to have a certain effect on how we write our reactions. So here, the strong base here is sodium hydroxide, and we're going to name that like an ionic substance because strong bases are typically ionic substances. And so if we look at the name of an ionic substance, we can break the name down and get the ions from the name. And so the two parts of the name are the two ions together. So we have sodium here, and since sodium is Na, and we know that sodium has a plus charge on it. And how do we know that sodium has a plus charge? There's a couple of ways that we can go about this. The first way is to just know the general rule is that if you have elements in groups 1A, 2A, and 3A of the main group elements, their charges, their positive charges are going to be equal to their group numbers. So if you're in group 1, if you're in group 1A, then you have a positive 1 charge. If you're in group 2A, you have a positive 2 charge, and so on. So sodium is in group 1, so we know it has a positive 1 charge. The other way and the better way is to just keep in mind and understand the structure of the atom and the valence electrons of the atom. And so we know that atoms in the groups, the main group elements, their valence electrons are equal to their group number. So if you're in 1A, then you have one valence electron. If you're in 2A, you have two valence electrons. If you're in 6A, you have six valence electrons, 7A, you have seven valence electrons, and so on. So if you keep that in mind, then and you also keep in mind that atoms want to gain or lose electrons to be like your noble gas, to have a noble gas configuration, and that noble gases have a full outer shell, which is typically 8 electrons. Then you can see that sodium here has one valence electron because it's in group 1. And so it's very easy for it to lose that one electron to have a full outer shell. So when it loses that one electron, it loses that negative charge. And so now there's a proton in the nucleus that is not being balanced by that negative charge. And so you have a positive charge that's not balanced. And that's where the plus charge comes in. So we have a +1 charge here. The hydroxide ion is a polyatomic ion that is OH minus. I'm sure your teacher has given you some sort of list of polyatomic ions to memorize. So you're going to need to know those in order to write the formulas for some of these substances. And so I have a video on how to remember the polyatomic ions, and how I go over patterns that might help you to do that. So if you're interested in that, so go to my video and take a look. So here we have hydroxide and sodium. So hydroxide has a -1 charge, the sodium has a +1 charge. And so since when you're making your formula, you need to make sure that the ions are balanced, the charges are balanced. And so here we have a +1, -1, and so all you need is one of each to make your formula. So you have NaOH. You could also do the crisscross method, right? So you have a 1 here and a 1 there. And so this would be a 1 there, and this would be a 1 here. And so you get 1 to 1, and you get the same thing. So here we have NaOH plus, and now nitric acid. So nitric acid, um, we can tell that this is a oxy acid because of the IC ending. Typically, oxy acids will have an OUS ending or an IC ending. And if you remember that when you're naming an acid, if you add IC to the end of it, that means that the polyatomic ion from which this acid is based came from an 8 ending of the polyatomic ion. So if you have an ATE ending, an 8 ending in your polyatomic ion for the acid, then that's going to be an IC ending in the name of the acid. If you have an ITE ending in the polyatomic ion that forms the acid, then that's going to have the OUS ending for that acid in the name of that acid. So here we have an IC ending. So that means that the polyatomic ion from which that this acid is based is an ATE ending, and the NITR tells us that we're dealing with a nitrogen. So we have a nitrogen-based polyatomic ion. So that's going to be nitrate. So nitrate. So NIRT, the NITR is the beginning of nitrite, and we know that this is nitrate because of the IC ending. So we have that as our nitrate ion. And so the acid is when we add hydrogens to this to balance the charge. And if we think of hydrogen as having an H plus on there, so we need enough H pluses to balance the charge. We have a -1 here, so we need only one hydrogen to balance the charge. So that is a 1-to-1, and that gives us our formula. So that's going to be HNO3. And the acid and base in the reactions are typically aqueous. And we can figure out that the hydroxide ion is aqueous, it's soluble. We could use our solubility rules, right, to do that. We could look at the solubility rules, and we know that from the solubility rules, it says that, where does it say about hydroxides? Yeah, it says all metal hydroxides and metal oxides are insoluble except when you have a group 1A metal with the hydroxide. So here we have a group 1A metal, so it is aqueous. And this is going to be aqueous as well. The acid base are going to be typically aqueous when you're mixing them. Usually you have a beaker of acid and a beaker of base, and you mix them together to get their reaction. Okay, so here we have our reactants. And so now we need to find our products. So we're going to do that right now. And so the first thing you want to know is when you have an acid-base reaction, this is an ionic compound. So, but this is not an ionic compound. So this is a typically, this is kind of a special category on its own. It's a molecular compound that actually breaks up and ionizes when you put it in water. So this will break apart in water. So we can think of this as an ionic substance because it will ionize. And so because we have this ionic substance and we have something that breaks up into ions, we could think of this as a double displacement reaction. So remember, whenever you have two ionic substances, that's a dead giveaway that you have a double displacement or double replacement reaction. And so you could figure out the products by putting the ions together in the same way that you would normally do with your double displacement reactions. And so how do you do that? Well, you put the inside ions together. So in this case, the hydroxide ion is going to go with the H plus ion, and the sodium ion is going to go with the nitrate ion. And so you put those together, and so the Na and the nitrate, the sodium and the nitrate, this is a -1, this is a +1, so those are going to be a 1-to-1. So that's going to be NaNO3 plus, and then you have the high H plus and the OH, that's going to come together and you're going to get water. So you got H2O. And so this is going to be liquid. So water is a liquid. And we're going to need to balance this equation, make sure it's balanced, and write the states for all of them. We have the state for this one. We have to check that out and see if that's a solid or aqueous. So here we have, let's go ahead and balance this. We have one sodium here, so that's balanced. We have nitrate, one nitrate here, and we have one nitrate there, so that's balanced. And we have one hydrogen and one OH. That's going to come together to form one water, and we have one water here. We could count them individually too. So we have two hydrogens, and we have two hydrogens, and we have one oxygen from the OH, and there's the one H. So we know that the oxygens from here came from the NO3 here, so we don't need to worry about those. So we already took care of that. So our equation is balanced. So the next thing is to decide or determine what state this is in. And so we're going to need our solubility chart or solubility rules. And when you look on your solubility rules, it says that all nitrates are soluble. There really are no exceptions. So this is a nitrate. So this is going to be aqueous. So that is our reaction. Okay, so now once we have our reaction, our equation, this is our balanced molecular equation. And so now the next thing is to get our complete ionic equation. And so remember, the complete ionic equation is where you take anything that is aqueous and you split it up into its ions, because in reality, the ions are not together, they are separated, they're dissolved, and they're floating around separate from each other. So the complete ionic equation kind of creates that realistic representation of what actually is happening in the beakers. So if we imagine that we have sodium hydroxide in a beaker, these ions are going to be separated, and so we're just going to separate the ions, Na plus, aqueous. And notice that when I separate the ions, I'm writing the charge with the ions. And so we don't write the charge in the formulas, but we do when we separate the ions. And so that's going to be added to, and we have our hydroxide ion aqueous. And then we're going to do the same thing. So the H and the NO3 are going to be actually broken apart. One thing I forgot to mention is that one of the thing we have to recognize is that this is a strong base and this is a strong acid. And what does that mean to have a strong base and a strong acid? Well, the strong word refers to the fact that both of these, when you throw them in water, are going to dissociate or ionize completely in water, so that you don't have really any of this together in water. All you have in water for the most part is the separated ions. You don't have any of this together and you don't have any of this together. They're all completely separated in water. So the H is going to be your H plus aqueous, and you're going to have NO3 minus aqueous. So in the beaker of your nitric acid, this is the only thing that you have in solution. You don't have the HNO3 together in solution. You just have this because it's a strong acid. And again, you don't have NaOH together in your beaker. You only have these two species separated, floating around in water. So now we can do our product. And so again, we have our sodium sodium nitrate aqueous. So those are going to be separated. So we have Na plus aqueous plus NO3 aqueous. And then for water, anytime you have a solid, liquid, or gas that forms, those are going to stay together. You're not going to break that apart. So water stays together as water. So that's going to be H2O liquid. Okay, so now this is our complete ionic equation. So we have our complete ionic equation for this strong acid, strong base reaction. And so the next thing is to get your net ionic equation. And to get your net ionic equation, that's where you have to remove something from the equation. And what we're removing is the spectator ions. So just like in your paycheck, you have your net pay. That net pay is when taxes are removed. So when we talk about a net ionic equation, that's when your spectator ions are removed. And the spectator ions are the ions that are not involved in the reaction. They don't form any product. So there's a couple of ways you can identify your spectator ion. One way is to go to your product that's formed. So here we have liquid water. That's the product that's formed. And so what formed that product? That was the H plus and the OH minus. So those we want to keep. The others we're going to get rid of. Another way that you can identify your spectator ions is to look at both sides of your equation and see what stays in the same state, right? So here we have sodium plus aqueous, and here we have 1 sodium plus aqueous. That's in the same state. It doesn't change. So that would be a spectator ion. We could get rid of that. And the same thing for the nitrate. The nitrate aqueous is also a spectator ion because we have NO3 minus in aqueous form here, and we have NO3 minus in the aqueous form here. So that would be a spectator ion. And you'll notice that they're not involved in the formation of water, so we can get rid of those. So our sodium goes away, and our nitrate goes away. And so now all we do is we write what's left. So we have our OH minus aqueous plus our H plus aqueous, and that's going to form H2O liquid. And so this is the reaction that is occurring in your solution. And this is the typical reaction that occurs when you have a strong acid and a strong base. So whenever you have a strong acid and a strong base, your net ionic equation is always going to be OH minus, your hydroxide, plus your hydrogen ion is going to form water. That is the reaction that happens. And the rest of it is just ions floating in water. You got some sort of salt floating in water, but this is your ionic reaction. So notice here, when you have your complete ionic reaction or your balanced molecular reaction, you have a salt plus water. The salt is typically going to be aqueous, and your water is left over, and that's going to be liquid. So that is how you do a molecular, complete, and net ionic equation for a strong acid, strong base. I hope you enjoyed this video. I hope you learned from it. And if you like my video, please hit the like button, hit that button. Make sure you share with your friends, put a comment in the comment section, let me know what you think, and subscribe to my channel so you can get notifications. Hit that notification bell so you will be notified when I put out new videos, and you can check those out. Thanks for joining me. Have a great day.